طيب بسم الله الرحمن الرحيم. So last time we talked about how to calculate the bit rate using the noiseless channel. When there is no accountability for noise, the bit rate is simply 2 times the bandwidth times log 2 of L, where L is the number of voltage levels. So that's Nyquist. For the case of noisy channel, Shannon has provided a similar equation that accounts for the noise through what we have discussed before as the signal to noise ratio. So he said that the capacity or the maximum capacity that can be achieved on this channel in bits per second is actually the bandwidth times log 2 of 1 plus SNR, the signal to noise ratio. Okay? So for the case when the SNR is very high, so we can simply ignore that one. صح? We can say that one is negligible. So it becomes log 2 of SNR. Log 2 of SNR can be represented as log 10. And when you convert log 2 to log 10, it becomes log 10 of the SNR divided by log 10 of 2. Okay? So when you multiply by 10 here and 10 here, this is the SNR in dP. Okay? And this is clearly 3. So from here to here جاية من فكرة إيه؟ إن إحنا we neglect ال1. When we neglect ال1, it becomes SNR in decibel divided by 3. So sometimes this saves time, and we'll talk about scenarios where this equation actually saves you some time. Okay, so the question is, what is SNR that's considered high? It's basically when the SNR is above 30 dB. 30 dB which is as a ratio is above like 3,000 or 3,500 or something like that. So above 30, you can use that equation right away. An example: consider an extremely noisy channel. Extremely noisy channel معناها the channel dominates and the channel makes the signal totally unrecognizable, which in other words is represented by the fact that the SNR is 0. Anything divided by very, very large, it becomes close to 0. So if the SNR is 0, the maximum bitrate is 0, which makes sense because if the channel is extremely noisy, you cannot actually get any kind of bits recognizable. So that makes sense for the case of a very, very noisy type. For the case of signal to noise ratio, that's defined in decibel as 36. So if I give you the SNR in decibel and it's 36, so in that case you have two approaches to calculate the bit rate. Of course, I give you the bandwidth. The bandwidth is 2 megahertz. So the SNR in decibel is 10 log 10 of SNR as a ratio. So SNR as a ratio is 10 to the power SNR in decibel divided by 10. So first you have to calculate that ratio, and then you define or you substitute in the original equation, which is bandwidth times log 2 of 1 plus SNR as a ratio, right? So in that case, you can calculate the maximum bit rate or the capacity as 24 megabits per second. However, if you observe that 36 is already high, so you can save some time and say this is actually 2 megahertz times the SNR in decibel divided by 3 right away. So it becomes 12 times 2, which is 24 megabits per second. So I can get to the same answer quickly, okay? Just by observing the fact that the SNR in decibel is high. Of course, if I tell you that the SNR is in decibel is like 2 or 3, in that case, you have to take into consideration the original general equation, which is log 2 of 1 plus LSNR as a ratio. ماشي؟ طيب, that's what's explained here. So SNR plus 1 becomes SNR. So I can neglect the 1, and in that case, I can use that equation. طيب, I can combine the two theory, Shannon and the Nyquist. Shannon gives me the limits, the capacity or the maximum achievable bit rate given a signal to noise ratio, right? So if we have a channel with 1 megahertz bandwidth, the SNR for this channel is 63. Pay attention to the units here. This is 63 what? This is a ratio, it's unitless. If I put decibel, then this 63 is huge. But as a ratio, this 63 is low. It's actually very low. So what is the appropriate bit rate and the signal level? So the bit rate can be calculated using the SNR, using the Shannon equation, the Shannon equation. So the bandwidth is 1 megahertz times log 2 of 1 plus 63. 1 plus 63 is 64. Log 2 of 64 is 6, of course. So it becomes 6 megahertz, 6 megabits per second. So that's the capacity or the limit that Shannon gives us. Okay? طبعا, in reality, as we have discussed in Network 1, what we achieve in practically on the channel is much less due to many reasons, and we called it throughput, or the actual bits per second that can be transmitted over the line. And we said that this is, in many cases, below the bandwidth, which is the maximum bit rate that can be sent over the line. We'll talk about the fact that the bandwidth can be defined as hertz or as bits per second. So this 60 megabits per second is very hard to achieve. It's impossible to achieve. So if we were to assume that a typical bit rate in that case would be less than 6, so we assume it's 4. So in that case, we know that the bandwidth is 1 megahertz. So through the Nyquist equation, we can get to the number of voltage levels that we need. In other words, it gives you an indication about the technology that you need to use in terms of the number of voltage levels in order to achieve, on the average, 4 megabits per second on a channel that's 6 megabits per second as a theoretical limit. Okay? So in that case, you need L equals to 4 or 4 different voltage levels. Or in other words, you need to represent each, how many bits? 2 bits as, each 2 bits will be represented by a voltage level. صح كده? Each 2 bits will be represented by a voltage level. So in that case, we have 4 different voltage levels, or L equal to 4. So if L equal to 4, 2 times 1 megahertz times 2, which will give us 4 megabits per second, and this is the achievable bit rate that you can get. Okay, مفهوم كده? So that's how you can combine both the Shannon equation and Nyquist equation. Of course, the difference between the 6 and the 4, I have to give it to you, or I have to give you some indication how to calculate it. So I tell you, مثلا, for example, the the typical bit rate is مثلا 80% of the maximum bit rate. Okay, so in that case you can calculate the 4 based on the maximum bit rate achievable by the Shannon equation. طب in terms of performance matrix that we will need these performance matrix later on in many ways. So we talked about the bandwidth and we know what throughput is. صح? We talked about the bandwidth as we defined it, which is the difference between the maximum frequency and the lowest frequency. صح? That's in hertz. But we can calculate it as bits per second based on the Nyquist equation. So from Nyquist equation, we can calculate it as bits per second. And we need to also talk about the latency or the delay, and we need to talk about these performance metrics. So in hertz, bandwidth in hertz, so this bandwidth in hertz is simply the range of frequencies between the maximum frequency and the lowest frequency for any composite signal. Okay, so we discussed that before. But this bandwidth can be defined in bits per second. In bits per second, we can use the Nyquist equation, which tells us that the bandwidth in terms of rate, bits per second, yani, equals to 2 times the bandwidth in terms of hertz times log 2 of L. So the two are proportional to each other based on this equation. Okay? So if I give you a bandwidth in hertz and I tell you the number of levels, you should be able to calculate the bandwidth in bits per second, which is actually the rate. Type. So the bandwidth can be defined as hertz or as bits per second. An example, the bandwidth of a subscriber line or ADSL yani, is 4 kilohertz for voice or data. The bandwidth of this line in data transmission in terms of bits per second is 56,000 bits per second. So this is calculated based on what? Based on the fact that this 56,000 is actually 2 times 4,000 log 2 of L. So what's L بقى? L أنا بقول لك L مش So 56 divided by 8 is a
4.5. 56 divided by 8,000.
56 divided by 8. Now 56,000 divided by 8,000. 7. So the number of levels is 128 different voltage levels. So using a technology that allows us to have each 7 bits represented by 1 voltage level, and we have 128 voltage levels, in that case, we can achieve 56 kilohertz in a channel that has a bandwidth in hertz that's 4 kilohertz. Okay? And that's not accounting for any kind of noise or any other impairments. Okay? So that's so now if I tell you that I want double that bit rate, but using the same bandwidth. So in that case, you have to increase the number of levels. Okay? So if I tell you that I need to double that bit rate somehow, then you have 2 options. Either you increase the voltage levels or you increase the bandwidth. The bandwidth is directly proportional. So if you double the bandwidth, you double the bit rate. ماشي? The voltage levels are logarithmic, proportional to the logarithm of the voltage levels. So I have to increase the voltage level. I have to increase the number of voltage levels يعني multiple times in order to get the bit rate increase. طيب, the throughput in 455 we define the throughput as the actual number of bits that you can get through in this transmission medium, and this is in many cases much يعني below, significantly below the capacity or the bandwidth in terms of bits per second. صح? And this is due to many reasons back. Due to the overwhelming, the receiver cannot cope with the bit rate that I'm sending. The network has some links that has like some bottlenecks. Many things, due to many things, or any kind of error that happens on the transmission line. And in many cases, so if we talk about this example, a network with a bandwidth of 10 megabits per second can pass only on average 12,000 frames per minute. Frames, يعني. Each frame is 10,000 bits. So 10,000 bits times 12,000, that's 120 or 128 or 12 megabits per minute. So if I wanted to get it per second, I have to divide by 60. So it becomes 2 megabits per second. 2 megabits per second is only 20% of the actual bandwidth. And that's practical, actually. This is practical. In practice, yes, the throughput is significantly less, and we get this. يعني احنا, most of us, we have the plan with Orido 10 megabits per second. But if you get more than 2 megabits per second, you're very lucky. يعني if you have no network load whatsoever and everything is fine, يعني what you get is typically less than 2 megabits per second, even though your plan theoretically is 10 megabits per second. So the throughput is sometimes 20%, 30%, depending on what technology you are using in the data link layer, depending on the probability of error over this transmission line, depending on many things. Okay? So that's the bandwidth and throughput. Bandwidth, we talked about it in terms of hertz or in terms of bits per second. The throughput is the actual amount of bits that you can send over the line. That's the practical amount of bits that you can get over the line. The delay has different components. Delay, any frame that gets transmitted, it encounters 4 different components of delay. And in order for you to really visualize and get the feeling of these delays, we can try to draw this graph. So if I tell you that you have a node, this node will have a queue. This queue lines up the frames or the packets in this way. Okay? So then this node will take one packet or one frame at a time, and then we'll process it and we'll try to send it over the line. When it sends it over the line, we can visualize that as you have like a pipe. This pipe, the width represents the pipe. Bandwidth, bravo عليك. The bandwidth of this pipe, whether in bits per second or in hertz. Okay? Then we send these frames over the line. يعني ايه send this frame over the line? We actually get the bits, we convert it into digital signal or analog signal, depending on what type of transmission we're talking about, whether it's baseband transmission or broadband transmission, right? And we send it over the line as analog signal or digital signal in the baseband, right? So it becomes a signal in that case. This signal, on the receiver side, this signal has to propagate, has to travel through the transmission line until it goes to the receiver. So this is the sender, and this is the receiver. Okay? So that's the scenario. That's the scenario that any frame or a packet goes through from the time it's created at the data link layer or at the network layer until it arrives at the receiver. At the receiver side, we'll have to do the reverse operation. We'll have to convert from digital signal or in the baseband or analog signal in the broadband into bits. These bits will have to be inserted in the queue, and then the node will have to read it from the queue. Okay? So in that case, we can talk about these components of delay. So the wait time inside that queue is what we call the queuing delay. So queuing delay is the wait time that a frame or a packet stays in the queue. ليه بقول frame or packet؟ لأن in the network layer there is a queue, in the data link layer there is a queue. Okay? Then, whether it's a switch or a router, it will take the packet and it will process it. يعني process it? Look at the header, process the fields of the header and so on and so forth until it figures out that, okay, I need to send this frame or this packet on a specific transmission line, which is wireless or wired, or if it's a router, it has multiple output interfaces and so on. Right? This is what we call processing time. So luckily, you don't have to calculate both of these. And in many cases, even if I want you to account for them, I have to give them to you. Why? Because these quantities are in many cases based on statistical probabilities and many things. Because the queuing time, how can you calculate it? It's based, you can enter to the bank and there is no one in the line, or you can enter to the bank and there are 1,000 people in the line. So it's very tricky to actually calculate. And in many cases, you do that in the master level where we have to use probabilities and so on and so forth. Processing delay is the same thing. And it's usually, in many cases, negligible, really. It's in the order of nanoseconds. So it can be neglected compared to the other components. So the transmission the transmission delay and the propagation delay are the most important two components that we need to calculate. The transmission delay is proportional to what? It's proportional to the width of this pipe, the band, right? And also proportional to the size of the bits or the size of the frame or the packet. So in that case, this is the L over the bandwidth in bits per second. Okay? Propagation delay is the time that the signal takes to travel from the beginning of the line until it reaches to the end of the line, which is the distance divided by speed. Time is the distance divided by the speed. ماشي? So these are the four different components of the delay. We have the queuing delay, processing delay, transmission delay, and the propagation delay.
So the medium speed, صح?
It's not يعني the speed of the signal in this medium, yes, which is in many cases close to the speed of light, which is around 3 and sometimes 2.5, something like that. 2.5 طبعا times 8 to the power 8 times 10 to the power 8. Sorry. تمام كده؟ So these are the four components of the delay. The most important ones are the transmission delay and the propagation delay. So as an example, what is the propagation time if the distance between the 2 points is 12,000 kilometers? So obviously this is like an under-marine cable or يعني cross-Atlantic kind of transmission medium. right? It's very, very long. If the propagation speed is 2.4 times 10 to the power 8. That's typical speeds in this kind of, so this is like sort of a fiber optic cable that spans cross-Atlantic under the ocean or something like that. Okay, so we can calculate the propagation speed as the distance divided by the speed. So the distance is 12,000 kilometers, so we have to multiply by 1,000, which is 12 times 10 to the power 6. And 2.4 times 10 to the power 8, so the answer is 50 millisecond, huh? Millisecond. Okay, so this ratio is actually 0.05 seconds. So we multiply by 1,000, we get it in millisecond. So 50 millisecond is enough for a signal, whether it's a digital signal or analog signal, to travel through a fiber optic under the ocean for a distance of 12,000 kilometers. That's practical. These are practical numbers on average. Okay? And 50 millisecond, by the way, in networks is a significant amount of delay. Okay? So in that same line, if I tell you that the bandwidth is 1 gigabit per second, which is fast Ethernet, okay, and I tell you that you have a length of the message, which is typically like an email or something like this, and this message has a length of 2.5 kilobyte. So what is the transmission delay and what is the propagation delay? So we calculated the propagation delay already, صح؟ أنت عندك سؤال؟
Yeah, just make the units the same.
Yeah, so yeah, yes, this is very important, huh? And you have to really pay attention to the units, especially when you have a ratio. You have to make sure that the ratio of the numerator is equivalent to the denominator. So we calculated already the propagation delay is 50 milliseconds. So when we calculate the transmission delay is length divided by the bandwidth. صح? When you insert a flow of water into the pipe, okay, then the time required is proportional to the width of that pipe and the amount of water that you are inserting into the pipe, which is the length of the packets. So it's typically 2.5 times 1,000, and this is bytes, so we have to convert it to bits, divided by the bandwidth, which is 10 to the power 9. So as you can see here, this time is 0.02 millisecond, which is in fact negligible compared to this. So we're using fast Ethernet over fiber optic that spans 12,000 kilometers. So that's practical. So the transmission delay in that case is negligible compared to the propagation delay. But this is based on the fact that you are sending an email. So if the distance of this line gets much shorter, which is typically, the LAN is typically like 100 meters, right? So for 100 meters, in that case, the propagation delay becomes a negligible compared to the transmission delay. All right? So the bottleneck is sometimes the propagation delay, if we're talking about submarine communication or underwater kind of communication for a long time, or maybe the bottleneck would be the transmission line if we're talking about LANs. If we're talking about LANs, usually we neglect the propagation delay and we calculate the transmission delay. So this example talks about that. So if the message length increases, and now we're talking about an image, and the bandwidth decreases. So this 50 millisecond is the same, but now the transmission time is the length of this image, which is 5 times 10 to the power 6 times 8, طبعا, because we're talking about bytes, divided by 1 megabits per second bandwidth in that case. So it becomes 40 seconds. So it's clear now that 40 seconds is much more than the propagation delay, and the propagation delay becomes negligible in that case. So in these types of scenarios, we can simply ignore the propagation delay and calculate the transmission delay. The fourth and last performance metric, which is what we call the bandwidth delay product. The bandwidth delay product is one interesting metric that we need to understand what it represents exactly. So the bandwidth is, as we said, bits per second times the delay, which is in seconds. So what we get is bits. So what is these bits really? These bits are the number of bits that can fill the transmission line. The number of bits that can fill the transmission line. So if I transfer the bits one after the other, okay? So after finishing transferring the whole burst, then these bits are the bits that can fill the line, and these are specified by the bandwidth times the delay. So the delay that I take to send these bits multiplied by the bandwidth, this product will give me the amount of bits that can fill this line. In other words, if we want to visualize this more, the bandwidth represents the width of the pipe, right? The delay represents what? The length of this pipe. Okay? So if I want to send a burst, I can send each bit, and by the time I finish this, which is the delay, I will have calculated the bandwidth, which is the area of the, or the width of the pipe, multiplied by the delay, which is the length of the pipe. So in other words, I'm calculating the volume. صح? The volume of this pipe, or in other words, the amount of bits that can fill the line. So the bandwidth delay product gives us the number of bits that can fill the entire line.
It should be 25. We're sending 5 bits per second, not 4 bits per second. 5. 5 bits.
لا لا
Sending 5
لا 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 احنا
per second.
لا احنا bandwidth times the delay.
Okay, but
The bandwidth delay product, so you have
in the image, it's 5 bits, 5 bits.
okay.
So it should be 5 multiplied by 5.
Yes.
So that one is 5 bits per 1 second.
Yes, so so either has this has to, you're right. So either you have to make this 5, or you make the number of bits that you can send in 1 second 4. So yes, so this has to be 5 in order to match. صح, مظبوط, you're right. So 5 times 5 will give you 25 different bits, and these 25 different bits can fill the line, which is what we call the bandwidth delay product. So this bandwidth delay product is also one of the matrix that we can use to calculate the number of bits that can fill the line, or in other words, the volume of the pipe. أيوة.
دكتور نحضر يعني the bits are just entered.
لا there is no distinction between the two. هو بس بيغير الألوان يعني. هو بيقول لك يعني those are the head number of bits, and then after that the other 5 bits, and then after that the other 5 bits, and then after this the other 5 bits. So there is no distinction. That's what this color represents. So this is chapter 3. So in chapter 3, we talked about the number of matrix that we can use. We talked about the noiseless channel, the noisy channel, and how we calculate the capacity of the link. And in chapter 3, we mentioned a lot the fact that when we convert zeros into a digital signal, صح? We mentioned that a lot. So in chapter 4, we talk about how we represent these zeros into a digital signal. In chapter 5, we talk about how to convert these zeros or these zeros and ones into analog signal. So this is the digital transmission, in which case we define it as the baseband transmission, where we convert the zeros and ones into a digital signal that starts from 0, and ideally it ends at infinity in terms of frequency, صح? So that's the baseband transmission. So the number of ways that we can represent the zeros and ones into a digital signal is actually enormous. We studied 2 of these in Network 1. So in Network 1, in fact, we have studied 2 of the digital transmission techniques where we converted the zeros and ones into a specific digital signal. So we studied about Manchester encoding, bravo عليك, and non-return to 0. Yeah. So these are not the only techniques that we can use, and there are tons of other techniques that we can use, and we'll study a lot more than these 2. We'll study many more techniques more than these 2. Also, all these techniques, they in fact line or they are under one category, which we call it line coding techniques. Okay, where we represent a group of bits into digital signal. So that's what this chapter talks about. So line coding and decoding in general talks about the fact that from bits we can convert it to digital signal. When we convert it to digital signal like this, typically we have 0 frequency components, and because it's a digital signal, we have very high range of frequency at infinity, but we said that there are some number of approximations that we have to do. We talked about that in previous.
The digital signal we are talking about is only 2 levels, right?
Not necessarily, no. Any number of levels will still be a digital signal, صح? We'll talk about that in a minute. Okay? But in other words, here we'll talk very often about some data element, which could be 1, or could be 2, could be 3. Okay? So some data element. And we need to convert that to a signal element. So if we have 1 binary digit and we want to convert it to digital signal, then we need how many levels? 2. If we need to represent 2 bits, we need 4 different signal elements. ماشي? And so on. So this is what we call line coding or decoding. At the receiver side, of course, we have to do the reverse operation. We have to convert from digital signal to bits. So before we can get to that, we need to define certain very important matrix, actually. One of them is the ratio R. R is very simple. It's the ratio between the data elements and the signal elements. So if we have 1 data element represented by 1 signal element, okay? So in that case, we need 2 different signal elements. So for example, 1 positive and 1 negative. And in that case, R is 1 over 1 is 1. Okay? In some cases, we actually need R to be less than 1. In other words, we represent 1 bit by 2 different signal elements within the same bit. An example is Manchester. And we talked about many advantages that Manchester has over the non-return to 0. We talked about these advantages. We'll study this again now, and we'll talk about these advantages again. And we'll understand it in a lot more depth. Okay? But we can have the reverse scenario, where we have 1 signal element to represent 2 data elements. In that case, R is 2. R is 2. And by doing that, we can have more bit rates, right? According to Nyquist, we can have more bit rates in the same bandwidth because we can use one signal element to represent 2 bits. So the bit rates will be high in that case. However, as we have discussed, of course, increasing these signal, the number of levels will have some disadvantages. We can have, in general, any arbitrary number of bits that gets represented by arbitrary number of signal element combination. So that scenario is interesting. So we have 5 different bits represented by 3 signal elements. Okay? So here, how many different combinations of signal elements I need at the minimum?
Thank you.
When I have 5 bits that gets represented by 3 different signal elements, how many signal element combinations I need? Different. لا يا راجل 5 bits. لو قلت لك 5 bits represented by 1 signal element بس يبقى how many voltage levels you need؟ يا راجل.
For 5 bits, 1 single element.
أيوه. How many levels you need؟
1.
How many levels؟ 32 صح؟ طيب إذا قلت لك بقى لا هم بقى مش 1 element ده هم 2 برضه هم 32 different signal element combinations. لو قلت لك ان هم 3 برضه هم they have to be 32 different signal element combinations. Okay? So the voltage levels can be reduced and increase the number of a signal elements. Okay? So in other words, in all cases you need at minimum 32 different signal element combinations. Again, we'll talk about how. Yani, we'll talk in details about how do we do this. طيب. So we need to define طبعا the data rate, and the data rate in bits per second, we defined that before, which is the number of bits that we can send in 1 second. صح? So that's given, which is n. We call it n. This is the number of bits per second. Number of bits that we can send in 1 second. That's easy. So what is the signal rate? Or in many cases we call it the baud rate or pulse rate. That definition here is a little bit inaccurate. I'll tell you why. This is the number of signal elements. لا هي بقى the number of signal elements changes. I would put the word changes here. Sent in 1 second. Why? Because the simple example. Because the signal rate is actually the frequency or the number of changes that you have in 1 second. Because as simply, if I'm sending 0, 0, 0, using a simple non-return to 0, okay, the signal becomes fixed. What is the frequency of this signal? It's 0. But what is the number of signal elements per second? It's not 0. It's not 0. What number of signal elements per second? R is 1, yes, but the number of signal elements per second is not 0, صح? ليه احنا قلنا the signal rate is 0? Because the changes, there's no changes in this signal representation. صح? So I think the word changes here is to make this definition accurate, more accurate. This will help you actually understand why, when we say the signal rate is the bit rate divided by R. ليه divided by R? And of course, if we have number of signal elements that represent less number of data elements, the frequency required will be higher. صح? صح؟ And if we have less number of signal elements that represent the same number of data elements, the frequency required will be lower. So that's why it's proportional to 1 over r. ماشي؟ فn over r دي مفهومة. فين بقى السي دي؟ سي دي قال لك دي case factor. This case factor is arbitrary and it will be given. هي based على ايه اصلا؟ هي based على الكونسبت ده. ان انا when I talk about certain stream of bits, sometimes I have the extreme case where I have all zeros, which means the signal will have zero frequency. And in some cases I have 0, 1, 0. So I have a signal like this. So the number of changes in this 3-bit duration becomes 2 changes. صح? This is the other extreme. Okay? So the actual frequency required in terms of signal rate or baud rate depends on the probability of the different bit pattern, whether it's 000 or 010 or 110 or اللي احنا اتكلمنا عليها قبل كده. Okay? So the actual signal rate is somewhere in between, and it's accounted for by this case factor. So this case factor gives you the average baud rate or signal rate given the n, which is fixed, and r, which is fixed. Okay? So even if n is fixed and r is fixed, the signal rate depends on what are these bits. If it's 000, it's different from 010, is different from 111, is different from. So you have to try all the different combinations of these bits and calculate the average for all these cases. So that's what this C will give you. So C will give you the average signal rate based on all the possible combinations of these bits. مفهومة ولا ماشي؟ مفهومة؟ عشان just to understand it, you have extreme cases. You have when you have 000 or 111, the signal rate is 0, صح? But when you have changes at every single bit, the frequency required will be high. Right? So C is typically less than 1. It's definitely less than 1. And in many cases it's half. ماشي؟ واضح كده؟ Luckily you will be given C. يعني أنا مش هقول لك بقى يعني I will give you C. ماشي؟ من الآخر I will give you this C. But this is to understand where this case factor came from. It came from the fact that we have different combinations of these bits that will change the signal rate. So I have to calculate the average based on all the different combinations. In some cases, I have certain bit patterns with higher probability. So in that case, C might be slightly more than half. Okay? So an example, if a signal is carrying data in which each data element is represented by one signal element. So R is 1, so we don't have to worry about R. And the bit rate in that case is 100 kilobits per second. What is the average value of the baud rate? The average value of the baud rate is definitely not when the case factor is 0, not when the case factor is 1. It's somewhere in between, and we can consider C as half. Of course, I will not leave you to assume. In that case, I have to make the question explicit, and I have to give you C. So C in that case is half, so which is half the 1 kilobits per second, which is 50. We call it a baud. So the unit here is baud. Baud here measures the number of changes in the signal elements per second. Okay, كده? So baud represents the number of changes in the signal elements per second. واضح ولا الموضوع صعب؟ ماشي؟ ماشي الحال؟ which is yes, it's proportional to the frequency. ما هو الفريكونسي ما احنا قلنا rate of change per second. ماشي؟ طيب. So the baud rate is what actually affects the bandwidth in terms of hertz. ماشي؟ Not the bit rate. So the bandwidth itself is proportional to the signal baud rate. The bandwidth of the signal is proportional to the bit rate based on the case factor. So the minimum bandwidth is in fact the baud rate. So this average changes per second will be the minimum bandwidth. So the minimum bandwidth is calculated as this baud rate or this signal rate. The maximum can be when C equal 1 مثلا ولا حاجة. ماشي? Or when you have the worst case, that you have a change at every single bit. So I can give you this baud rate, and I ask you, given this baud rate or given this bandwidth of the of this line coding scheme, what is the maximum bit rate that you can achieve? So in that case, you can calculate the maximum bit rate as 1 over C times B times R. So given that this is the bandwidth that you have, what is the maximum bit rate that you can fit in that case? So which is the reverse of this equation. So N equals to 1 over C times R times this bandwidth.
Will any formulas be given to us, or do we have to memorize them? The formulas.
Yeah, that's a good question. يعني
Negotiate.
يعني in some cases يعني we had of course these simple equations you need to kind of know them, but in the exam يعني in some cases the university asks us to give you these equations and not having to memorize them, which I don't agree with specifically, but يعني in many cases we give you these equations.
Why don't you agree with it?
أنا?
No. Because us as engineers, we're not going to memorize this. Whenever we need to know an equation.
Because of the fact that you're an engineer, there are certain equations that you need to memorize them. يعني ما ينفعش اصلا واحد يقول لك احسب لي مثلا دي كام، اقول استنى بقى لما اروح اشوف المرجع واشوف مش عارف الايكويشن ده بيتعمل ازاي وكده. لا يعني there are some fundamentals that you need to be aware of.
Let's be honest يا دكتور، لما احنا نتخرج we get a job مش راح يجي لك okay solve this question يلا سلام عليكم.
لا in many cases لا in many cases يعني these are very simple equations. You can argue مثلا ايه what is the value of C? That I can understand. يعني that I can understand. انما لما اجي مثلا ادي لك minimum bandwidth واقول لك احسب البيت ريت، يعني it's very simple يعني. You just multiplying two quantities. In that case حتى you should do it in your mind and give me the answer right away. You don't have to really ولا go بقى المرجع ولا الكلام ده. يعني الحاجات ديت when you tell me okay I will tell you the answer tomorrow, I'll tell you okay you're fired يعني. You have the right to do that and I have the right to fire you. يعني when it comes to these fundamentals it's easy and it should be memorized.
Don't think about working with you.
نعم.
I shouldn't think about working with you.
لا I'm not the one who will fire you. طيب we talked about this phenomenon before, which is the lack of synchronization. We need to study the effect of this lack of synchronization between the transmitter and the receiver. When we talk about line coding schemes, we convert each data element to specific signal element. Okay? When we talk about data element to signal element, we have to use certain type of a clock, right? Which defines the duration of this bit as a signal element, right? So when we want to detect this bit at the receiver side, ideally, we need to use the exact same clock, right? If we can do that, then this bit will be also recognized as the exact same bit at the receiver side, assuming we don't have any channel impairments, right? But this is ideal. In practice, synchronizing clocks on two different machines is a very complicated issue. And in many cases, you need a third centralized clock to synchronize the clocks of all the participants. Okay? So practically, you have some kind of a clock drift. So as you can see, the clocks at the receiver side are slightly different. So what is the impact of this? This has two implications. At the receiver side, the receiver will now say, okay, this is one bit, and this is another bit. So what is this bit? Well, this bit, the voltage level is above 0, so it's a 1. So what is the second bit? I don't know.
The second bit?
Yeah, I don't know. Why? Why not 0? Why 1? I don't know. صح? So this bit might very well be recognized as 0 by mistake, or 1, which is also by mistake. صح? So that's the first implication, that some of these bits can be recognized in a wrong way. And this is drastic. This is a critical problem. صح? What is the other problem? The other problem is that how many bits are detected now?
Yeah, more bits.
Is maybe double. Or in other words, more bits than what has already been sent. So you send 1,000 bits, and the receiver receives 1,100 bits. Okay? So that's another implication to this synchronization problem. So synchronization can be very, very drastic. And that's why synchronization is a huge issue.
We don't use it. We use handshaking. Asynchronous.
لا synchronization is a big issue. It's a big issue. It's a big issue. Big issue. We will not study how to mitigate this synchronization issues as part of the course because it's, in many cases, very, very complicated. Very complicated.
If you use the same clock speed at the sender and the receiver, so
خلاص الحياة حلوة خلاص ما فيش مشكلة. There's no problem.
so
But
same clock
who
speed,
can guarantee this?
Same clock speed, but it's not synchronized. So
Yeah, even if it's shifted. Yeah, that's a good issue. Yeah, just the fact that the clock speed is the same, it doesn't mean that they are completely aligned.
you can get the same number of bits at the sender and the receiver.
Yes, but maybe all of them are wrong, or some of them are wrong, depending on how lucky you are. Okay? So even if you have the same clock speed, that doesn't guarantee that the bits will still be recognized correctly. If there is a slight shift, again, this might cause some problems at the receiver. Okay? That we just talked about here. Right? So in some bit durations, the voltage level will change. And it will cause the receiver to recognize the bit. So that's an example. In a digital transmission, the receiver clock is 0.1% faster. Yeah, there is a slight difference in terms of speed in the clock. So how many extra bits? And I didn't tell you how many bits will be in error, because this is very hard to calculate. We don't know. It depends on the stream of bits, how they look like. Okay? But we can calculate how many extra bits we need, because if we're talking about 0.1% faster, so this means that for how many bits I have one extra bit? For each 1,000 bits, I have one extra bit. يعني if I tell you this is 1% faster يبقى for each 100 bit I have 1 bit extra صح؟ 0.1 معناها for each 1000 bits I have 1 bit extra صح؟ So for each 1000 bits I have 1 bit extra. So if I have 1 million bits then I have 1000 extra bits I receive at the receiver. طبعا this is not the only problem. The other problem is that even those number of bits will not be correct, will not be all correct due to lack of synchronization. Why? Because of the wrong way. ماشي? So that's the implication of lack of synchronization. طب we'll stop here عشان next time inshallah we'll be synchronized with the other group.